Okay, so last week we were going over the concept of likelihood functions and also maximum likelihood estimation. And so before we really discuss a lot of other topics within maximum likelihood estimation and move on to our various optimization techniques that we're going to learn in this course, I thought it might be a good idea to review and make sure we really understand what's going on in likelihood functions and also familiarize ourselves with some of the sort of coding aspects or just visualizations of likelihood functions. So if you recall that in our notes we had an example where we basically let's assume that we observe, let's assume that we observe, two data points, just exactly n equals two data points. And the two data points we observe are x1 being 2 and x2 being 3. Okay. Further, we're going to make the assumption that these data are from normal distribution, right? So, like I said, so there's two data points that we are assuming, and we are also assuming that these are all coming from the normal distribution. Now, with this assumption, we have then defined our likelihood function. Recall that our likelihood function, assuming that the data are independent, we are assuming that they are coming from normal distribution. So the likelihood function is just going to be the density function evaluated at x1 times the density function evaluated at x2 at various given values of theta. So this likelihood function, so let me just write that this is the likelihood function. And then the downstairs, I'm going to draw the log likelihood function. So the likelihood function is just the product of the density functions at the actual data point that we have observed, x1 and x2, but evaluated at any value of theta. Okay, so it basically tells us how likely is a value of theta given that we have observed this data. Now, similarly, instead of the likelihood function, I can also define the log likelihood function. The log likelihood function, if I just take log, is going to be log of the densities. So this is log equals true of the density functions plus log of the other density function, other being the other data point, since I've only observed two data here. So log equals true, so log of the density function, and add all of these up. Adding because I've taken log now, so log of product is sum of logs. Now, once I've done this, I've set up my code to just visualize and evaluate and understand my likelihood function. So now in this line, what I'm doing, line 23, is I'm creating a grid of theta values, theta being the parameter values, and trying to basically then for each of those theta values. So if I run this line, and if I just look at the head of this line, this gives me a sequence of points from -1 in small increments so that the actual length of the whole vector is 500. And if I look at tail of theta, it should end at 6. Okay, so it's going to be a grid of values. And for each of those values, on the x-axis, I will plot the theta value. And on the y-axis, I'm going to plot the likelihood function, right? The likelihood evaluated at a given value of theta. So now once I do this, I can plot that. And once it does it, this is exactly what the likelihood function looks like. So in black, I have the likelihood of a particular value of theta having observed data x2 equals 3 and x1 equals 2 from a normal distribution. So what this is saying is that, listen, I obtained and noticed that I got two data points from a normal distribution with variance 1 of data being equal to 2 and 3. Given that I've observed this, how likely is it that theta equals -1 is a value of theta? Well, it looks like it's much smaller than other values of theta. And where is the value of theta that gives the largest value of the likelihood function? It's right in the middle over here, which happens in the middle of 2 and 3, in this case 2.5. So 2.5 becomes the maximum or the most likely value of theta, or the argument in theta that maximizes the likelihood function, and that gives me the maximum likelihood estimate. The other thing we discussed is often dealing with likelihood functions can be quite unwieldy because of the fact that there's a product term involved. And so taking derivatives with respect to theta can be quite cumbersome when you're dealing with products. So instead, what I'm going to show you now is if I plot the likelihood function and I also plot the log of the likelihood function. So in this particular first line of code, I'm going to plot the likelihood function. The second line of code, I'm going to plot the log likelihood function. I'm going to see that yes, the curves are going to be different as seen here. Okay. So in the black, I have the likelihood. Now, the thing is that now the axes are a little squished because the log is on a different scale and the likelihood is on a different scale. But we can still see the rough shape of the likelihood function. And I can also see the shape of the log likelihood function. But what's interesting is, although the shapes are different, notice that the place where these two curves are maximized remains the same. Okay. So notice how the argument in theta that maximizes both the log likelihood and the likelihood remains exactly the same, which is why if our goal is to just to find the argument that maximizes theta, I can just maximize the log of the likelihood instead of maximizing the likelihood. Okay, so I just wanted to make sure that we understood this particular aspect of likelihood functions. Now, there was another piece of sort of visual that we had in our notes, and that's also visualizing the variability in the likelihood function. So in that particular piece of code, what we were doing is what I do is I set a theta star to be equal to 5. Now, what I'm doing over here is I'm basically assuming that I know an actual value of theta. This value of theta is in some sense I'm playing the creator of the world, and I'm saying that for a particular model or for a particular data, the actual theta that will generate that data is 5. Okay. Now, in a real life situation, we don't know the actual values of the parameters that generate our data, which is why we do estimation and statistics. However, because we're on the computer, we can do this. So I'm going to set theta dot star, the true value of theta. Okay. So I'm here, I'm setting the true value of theta. And then once I've set it, I will forget that I know what the true value of theta is. I'm not going to remember it. And now I'm going to set a grid of values of theta 0 to 100, so 0 to a 10. And what I'm going to do is the following. For 100 times, I'm going to draw one data point. Okay, so there's going to be two different simulations I do. I'm going to draw one data point from a normal distribution with parameter theta dot star. So I'm going to mimic what we do in the real world when we go and get data. Okay, and that's going to be in my data. And for this data, I will then evaluate the log likelihood for each of these different values of theta. Okay, with standard deviation 1. So I'm assuming I know that the population variance and standard deviation are 1. But for the data observed, I will evaluate the likelihood given this observed data for different values of theta. And what I will get is then a vector of values. Okay, so when you get this code, please play around with it to see what's going on. But I will get a vector of values. For each value of theta, there will be a corresponding likelihood or log likelihood value. And the whole vector of values will be stored in the rth replication in likes.1 data. Similarly, I'm going to also do likes.hunt data, which is 100 data points, where instead of getting one data point, I'm going to get 100 data from the distribution that has theta star, or the true theta is 5, right? Which is going to be a normal distribution. And again, I will then calculate the log likelihood, which, because now there are 100 observations, this is now going to be the average log likelihood, sorry. This is now going to be, for each data point, I will calculate the d norm with option log equals true, but with mean equals these vector values of theta. But then I will add all of them up because I have 100 of these data points. I'll have a summation I going from 1 to 100 log of f. Okay. Okay, so what I'm going to do now is I'm going to run all of this. It's going to take a little bit of time. Done. And now I can plot each and every one of these values. So uh, what I'm doing now is I'm setting my grid. So on the x-axis, I have theta values. On the y-axis, I have the expected log likelihood. And this is for normal 5, comma 1 because theta dot star was 5. Okay. And now, for example, I'm not going to run this loop yet. I'll show you in a second. But if I just run this, if I say, well, for r equals 1, if I'm just going to go and plot the lines obtained with theta on the x-axis and the corresponding likelihood value, log likelihood value on the y-axis for one data point, that will be in red. And the lines obtained with theta on the x-axis and the corresponding log likelihood value on the y-axis. Okay, and actually what I can also do is I can do sys.sleep here just to show you an animation of what happens maybe at 0.2 seconds. Hopefully this will be captured in video reasonably. And I'm just going to run this and we'll see what happens. One by one, as R changes, it will go ahead and go into a new data that we had drawn and the new likelihood for that we would have obtained in each of these two steps and plot the corresponding likelihood function. Okay. See, slowly it goes and gets that data observation and plots the log likelihood function corresponding to it. The blues are the likelihood functions coming from 100 data points, and the reds are the likelihood functions coming from just one data point. And what I want you to understand here is that every time the actual population from which we have drawn is exactly the same. In each of these 100 replications, the population we are drawing from is still normal 5, 1. But every time we get a different red line for the one data point, and every time we get a different blue line for the 100 data point. Okay. And that is essentially because of the idea and the fact that the data are random, which means that the corresponding or resulting likelihood function is random as a function of the data that we've observed. Okay, so if the data changes, the likelihood function also changes, right? Which means that given a particular data that we've observed, we want to maximize that data or that likelihood that we have observed from the data that we have observed. Okay, so hopefully this idea makes sense. Again, play around with this code and you can also try and think about changing. So here we're doing normal distribution. You can try and change this to, let's say, the gamma distribution or the exponential distributions, etc. And try and see how the likelihood function changes as a function of, let's say, the number of data or so on, etc.